So here are some key words to take note of when it comes to stoichiometric questions. Stoichiometry itself has to do with the relationship that exists between the reactant and the product in a balanced chemical equation. That aspect is very essential. So if you are still having challenge with that area of balancing equation, it's important you study that again before you proceed. So we could be relating the amount of reactant with the amount of the product. It could be volume to mass. It could be amount to the number of particles. Any way it comes, everything borders around a balanced chemical equation and how the reactant and the product relate. For amounts, which is also known as moles, moles is talking about the number of particles that we have present in a particular substance. That particle in question now could be in form of atoms, it could be in form of ions, molecules, or electrons. Then, for 1 mole of any substance, they always contain Avogadro's number of particles. That is a constant, and the value is 6.02 times 10 raised to the power 23. That implies that if I have 1 mole of CO2, or 1 mole of HCl, or 1 mole of NO2, any of those, and many more, they will always have the same number of particles, which is the Avogadro's number. Then for molar mass, that is talking about the mass of each of the atom that makes up a particular compound. So when you are given CO2, for instance, CO2 is what you are given, and carbon has a mass of 12, while oxygen has a mass of 16. Those are the atomic masses. So if I want to know the molar mass of CO2, all I have to do is to add up the mass of each of the atoms of the elements in that compound. So there I have 1 carbon, so that would be 1 multiplied by 12, plus I have 2 oxygens, so that would be 2 multiplied by 16, and that will give me 12 plus 32, and that will result to 44. And the unit for molar mass is gram per mole. That is the mass for 1 mole of a substance. Then finally, molar volume of a gas. That is talking about the volume that a particular gas occupied. 1 mole of that gas, the volume it occupies under a standard condition of temperature and pressure. That is STP. So that volume is also a constant, and the value is 22.4 dm3. So that implies if I'm given any gas whatsoever, CO2, H2, O2, any gas, 1 mole of those gases will always have the same volume, and that value is 22.4 dm3. Going on, here are some basic quantities that is always very important to take note of when it comes to stoichiometry, and also their units. It is also very important to take note of these units, because occasionally when we get to calculation aspects, you will be given values and the units. Those units will help you know what quantity is being talked about. So here are some basic quantities we have under stoichiometry. For mass is a very common quantity. The unit is gram or kilogram. As far as calculation in chemistry is, we always base our calculations on gram. So even when you are given the value in kilogram, you convert a gram, knowing that 1,000 grams equals to 1 kilogram. So you can always convert your value from kilogram to gram by dividing your value by 1,000. Molar mass, as we talked about, the unit is gram per mole. Then the volume, that one is also a very common quantity. The unit is centimeter cube or dm cube. Dm cube can be converted to centimeter cube and vice versa, knowing that 1,000 centimeter cube equals to 1 dm cube. Sometimes the answer could be asked to be given in centimeter cube, and sometimes it could be in dm cube. Whichever way, you can always do your conversion knowing this conversion values. 1,000 centimeter cube equals to 1 dm cube. For molar volume, that one has been talked about in the previous slide too. That unit is dm cube per mole. Dm cube per mole, that's the volume for 1 mole of a particular gas. If that gas is measured under standard temperature and pressure, then the value is going to be 22.4 dm cube per mole. Then amount, that one too has been talked about in the previous slide. The unit is mole. So amount is moles. Molar concentration is mole per dm. We have two types of concentrations: molar concentration and mass concentration. For molar concentration, that is amount over volume. Amount over volume. So if the unit of amount is said to be moles and the unit for volume is dm cube, so the molar concentration is going to be mole per dm cube. Then for mass concentration, that will be mass over volume. So if the mass is measured in grams and volume is in dm cube, that will give us gram per dm cube for the volume, for the mass concentration of a particular substance. We use per dm cube because 1 dm cube is equivalent to 1000 centimeter cube. So if you don't want to say mole per dm cube, that means you want to say mole per 1000 centimeter cube. So better still, just say mole per dm cube for molar concentration and gram per dm cube for mass concentration. For us to determine the amount of a substance in a given equation, the amount is the same thing as the number of moles of that substance in the equation. So here, let's compare these parameters for the C2H4 in that equation and the oxygen in that equation. So the amount of C2H4 in that equation, that will be the number of moles. That number of moles will be the coefficient that's used to balance that particular compound or element in that equation. That is the number that's written just before the formula of that particular compound in the equation. So here we are talking about C2H4. So when nothing is written before the compound, of course, that means you have one of that particular compound. So the number of mole of C2H4 in that equation will be 1, which is also the amount of C2H4 in that equation. So the amount of this is 1. That of oxygen, we have 3 as the coefficient used to balance that oxygen to the equation. So the number of moles of oxygen will be 3. For the volume, also known as the molar volume, the volume of C2H4, always have it in mind that 1 mole of any gas whatsoever, we have a volume of 20.4 dm3 at standard temperature and pressure at STP. So it's a standard value to know. 1 mole of a gas equals 20.4 dm3. So for the C2H4 here, since we have 1 mole of that gas, so the volume is going to be 20.4 dm3. As for oxygen, since we have 3 moles of oxygen, so the volume of oxygen will be 3 multiplied by 20.4 dm3. We multiply that and we get the answer for the volume of oxygen. Now for the number of particles, 1 mole of a substance, we have Avogadro's number of particles. The Avogadro's constant is given as 6.02 times 10 to the power 23 particles. Sometimes we call it particles, at times we call it molecules or atoms. So to know the number of particles of C2H4 in that equation, since we have 1 mole of that particular gas, so the number of particles for that is going to be 1 multiplied by the Avogadro's number. So that will be 1 multiplied by 6.02 times 10 to the power 23 particles. As for the oxygen, since we have 3 moles of oxygen, so the number of particles for oxygen will be 3 multiplied by the 6.02 times 10 to the power 23 particles. And for the mass is just the sum of the mass of each atom of element of that particular substance that is being talked about. So talking about C2H4, in that equation, since you have 1 mole of C2H4, so that will be 1, we use that 1 to multiply the mass of each atom of the element in that particular compound. You have been given that carbon has a mass of 12, and there you have 2 atoms of carbon in C2H4, so that will be 12 multiplied by 2 plus the mass of 1 atom of hydrogen is 1, and we have 4 hydrogen atoms there, so we multiply that by 4. So doing that, you are going to have this to be equal to 24 plus 4, and the mass is going to be 28 grams. As for the oxygen, we have 3 moles of oxygen there, so that will be 3 We'll use that 3 to multiply the mass of the oxygen atom you have in that particular equation. And an atom of oxygen is having a mass of 16. And there you have 2 atoms of oxygen, so that will be 16 multiplied by 2. And that will now give you 3 multiplied by 32. And that will give you uh, 96 grams of oxygen. So this is how we determine the amount, the volume, the number of particles, as well as the mass of a particular substance in a given equation. So take a pause and try to figure out your own answers for these parameters asked about hydrogen gas in this given equation. And after which you can compare your answers with mine. So to talk about the number of moles of hydrogen in this equation, the number of moles is seen as amount. So that's the coefficient before the elements. So that will be 3 moles of hydrogen. The molar volume, since 1 mole of a gas is 22.4 gm3, so the molar volume of hydrogen there will be 3 multiplied by 22.4, and we get the answer in dm3. The number of particles, since we have 3 moles of the gas there, and 1 mole of a gas, we have Avogadro's number of particles. So that will make the number of particles together to be 3 multiplied by 6.02 times 10 to the power 23 particles. And the mass, since we have 3 moles of the gas there, so that's 3, we use that to multiply the atom of that particular element. And 1 atom of hydrogen is 1, and then you have 2 atoms of hydrogen, so that's 1 multiplied by 2, and that will give 3 multiplied by 2, which is 6 grams of hydrogen in that equation. This question says, what is the volume of nitrogen oxide? This is nitrogen oxide in the equation. What is the volume of that nitrogen oxide and the mass of copper 2 triazonitrate 5? This is copper 2 triazonitrate 5 in that equation. So let's start with that of nitrogen oxide. In that equation, what we have for nitrogen oxide is 4 moles of nitrogen oxide. 4 moles of NO2. That is the coefficient 4A. And remember, talking about the volume of a gas, 1 mole of a gas has a volume of 22.4 gm3. So now that you have 4 moles of nitrogen oxide, that means the volume of nitrogen oxide in that reaction will be 4 multiplied by 22.4 dm3. And that will give us 89.6 dm3 of nitrogen oxide. For the mass of copper 2 triazonitrate 5 in that equation, what we have in that equation is 2 moles of copper 2 triazonitrate 5. Now we're looking for the mass of that compound in the equation. So for that, the copper 2 triazonitrate 5, that will be Cu, plus in that compound we have 2 atoms of nitrogen. These 2 outside there will multiply everything you have in brackets. So we have 2 nitrogens altogether in that reaction, in that compound. Plus together we have 6 oxygens. That will be 3 multiplied by the 2 outside the brackets. That will be 6 oxygens. So this will multiply by the number of moles. Remember, we have 2 moles in that reaction, so that will multiply by 2. So that means we have 2 to brackets. The atomic mass of copper given is 63.5 plus 2 multiplied by 14 of nitrogen plus 6 multiplied by 16 of oxygen. So that will give us 2 into brackets 63.5 plus 28 plus that will be 96. So when this is multiplied, you are going to have 2 multiplied by 187.5 grams, and that will give us 375 grams. 375 grams of the copper nitrate, that will CuNO3. So that is the mass of copper 2 triazonitrate 5 in that equation. You should also be able to answer this question, so you can take a pause on the video and give your own answers and compare with mine. So here we are to determine the amounts of chlorine gas. This is the chlorine gas in that equation. and the number of molecules of hydrogen gas. Let's take it one at a time. For the amount of chlorine gas, remember that's still the same thing as the number of moles of chlorine gas in that equation. And what we have there is just 1 mole of chlorine gas. Don't forget that's the coefficient before the molecule in that equation. So the amount of the chlorine gas will be equal to 1 mole. Then for the number of molecules of hydrogen chloride gas, this is the hydrogen chloride gas, you have to determine the number of molecules. Don't forget 1 mole of a gas, we have Avogadro's number of molecules. And since we have 2 moles of hydrogen chloride gas there, so that means the number of molecules of HCl, that will be equal to 2 multiplied by the Avogadro's number, that will be 6.02 times 10 to the power 23 molecules. Don't forget, you can be asked whether the number of molecules or the number of particles or the number of atoms. Either of those three still talks about the Avogadro's constant. That's 1 mole of any gas, we have Avogadro's number of particles or molecules or atoms. That is it. So common formulas needed for calculation of stoichiometric questions are what I intend to give you here. And very common among them is one that has to do with amounts. Amounts, remember, it can be denoted by N, can be given as mass over molar mass. If your mass is measured in grams, and the molar mass, the unit is gram per mole. If you write this mathematically, that will be gram divided by gram over mole. So when you arrange that by changing that division to multiplication, you are going to arrive at gram multiplied by mole over gram. This will cancel this, and what you have left is mole, which is the unit for amount. So amount N can now be written as N equals to M for mass. Then you can represent molar mass by Nm. Another expression for amounts, N can also be given as volume over molar volume. This molar volume, volume over molar volume. The molar volume has a unit of dm cube per mole, dm cube per mole, and normal volume is dm cube over dm cube per mole. If you rearrange this to get to the final unit, you are going to observe that your dm cube is going to divide the dm cube, and you are going to result to mole, which is the unit for amount. So that means N, which is amount, is also written as, it's also calculated as volume over the molar volume. Let's represent molar volume by mv. Then also the amount can be given as the molar concentration, which has a unit of mole per dm cube times the volume in dm cube. By the time you multiply this unit together, you result to moles as the unit for amount. So that means N can also be written as CV, where C represents the molar concentration and V represents the volume of that particular substance. So three expressions together has been given for the calculation of amounts. So N can be equal to mass over molar mass. Also, N can be equal to volume over molar volume, and also N can be equal to molar concentration times volume in dm cube. Molar concentration is mole per dm cube, and that V, volume, must be in dm cube. Now another common expression that we use in calculation of stoichiometric question is one that has to do with concentration. Of course, like earlier discussed, concentration can be one of two. It's that we have it as mass concentration or we have it as molar concentration. For mass concentration, the unit is gram per dm cube, and molar concentration is mole per dm cube. So from this expression for mass concentration, the unit for mass concentration, which is gram per dm cube, that means our mass concentration, which can be denoted by this symbol, equals to gram over dm cube. And what we measure in grams is mass, and dm cube is volume. So that means mass concentration equals to mass over volume, while the molar concentration C equals to mole over dm cube. That's unit. What we measure in mole is amount, and what we measure in dm cube is volume. So if that is the case, we can say that C equals to amount over volume. Amount over volume for C, then mass over volume for mass concentration. Also, there is this other expression that connects the mass concentration, molar concentration, and molar mass together. And that expression is the mass concentration equals molar concentration times molar mass. If your mass concentration has a unit of gram per dm cube, so let's see when we multiply the unit of molar concentration and molar mass together, if we are going to result to the unit for mass concentration. So the unit for molar concentration is mole per dm cube, mole per dm cube, and this one is gram per mole. So mole per dm cube means mole over dm cube. Then multiplied by gram per mole means gram over mole. So if this mole cancel this mole, you are going to have gram over dm cube, which is something as gram per dm cube. So that means mass concentration can be given as molar concentration times molar mass. Molar mass. Then molar mass can actually be written also with just a capital N. A capital N, that will C M like this. Mass concentration equals to molar concentration times molar mass.